So our next speaker is Arkadi from Maastricht University, and he will talk about a joint paper with Yushensina, many co-authors, and the title is Games Characterizing limsup Functions and Baire Class 1 Functions. Arkadi, the screen is yours, please.
Thank you, Flesch. Thank you so much. First of all, I would like to thank all of you for coming today to this workshop, to this school. And of course, I would also like to thank the organizers for their very kind invitation to talk here and to present this paper and to be a part of this training school. It's really a pleasure and an honor. So thanks a lot. As Miklas mentioned, I'm in a very good company with this paper. So six authors, of which 5 of Hungarian origin. So I practiced during the break, but I'm sure there are, apart from Miklas and János, there are other Hungarians in the audience. So forgive me for butchering this beautiful language. So Márton Elekes, János Flesch, Viktor Kish, Donat Nagy, and Mark Poór are the co-authors of this paper. My plan is very simple. I'll start with an intro with a little bit of a motivation for limsup functions, for maybe even Baire class 1 functions, and for this talk. And then the main body of the talk is divided into 2 probably unequal parts, because part 2 on limsup functions will occupy more of our attention than the third part. It's absolutely not my intention to exhaust the 90-minute limit that we have, and it's quite likely that we will finish earlier, which means that there are there's plenty of room for questions. Okay, so this is one of a few talks where I start right away with related literature. Now, the reason I do so is that it helps me position this paper and this talk a little bit in the ocean of mathematical literature and in the ocean of game theoretic literature. Okay, so it's related to at least two related but distinct branches of literature. One is topological games. Now, what are topological games? Well, the term is very broad, okay, and it's hard to define precisely what topological games are, but usually topological games are first of all, they're games in the sense that Ron defined. So these are games of the type Martin studied. Okay, these are type of games that also Miklas talked about in his introductory word. And why topological? Well, I think that's because they would be used to resolve questions often coming from topology, but not always. So this talk roughly falls into this category of topological games, and at least to a certain extent, the next talk as well. But you'll see that in the following presentation, the games will be applied to questions coming from measure theory. So. I must say that topological games is a very old subject. In fact, it predates Martin and his theorem. These games have been used already by Banach and Mazur, and you will encounter these names if you look look in any of the textbooks on descriptive subtheory. Right, so this is the first branch of the literature. The second branch of the literature that's related to this talk are various characterizations of classes, of interesting classes of functions using games. Okay, so really these perhaps are these game characterizations. They're kind of topological games. Okay. And what kind of classes of functions people are interested in? Well, Baire functions, especially the ones in Baire class 1, received a lot of attention. I would like to add that this is a kind of literature to which not only descriptive subtheorists and not only mathematicians contributed, but also computer scientists. So Duparc and Caroy, I believe, are computer scientists and logicians. So this is a little bit of, you could say, almost an interdisciplinary field. Okay, so this is roughly where this paper belongs to. Now, the two classes of functions that we are interested in this paper are the limsup functions, so-called, and the Baire class 1 functions. And I think I will have to motivate the first and maybe not so much the second. Why is that? Well, because Baire class 1 functions really is the classical stuff. They bear the name of Baire. This is really one of the central concepts in subtheory. What about limsup functions? Where do they come from? Well, as it turns out, these limsup functions, so-called, they're also related to very well-known classes of functions. And in fact, there are various topological characterizations that are available. Implicitly, they appear in the book of Hausdorff already. So that's, you could say that this is also a known class, perhaps. From the point of view of game and gambling theory, that in fact is an important class of functions because many payoff functions are limsup functions. They would fall into this category. And roughly speaking, if you do think of a limsup function as a payoff function, then this payoff function would express a preference for obtaining good rewards infinitely often. I'll have an example to support this intuition. We could say that following Bill Sudderth, in fact, it was his. It's a quote from him. These limsup functions are more general than they appear. A number of classical objective functions used in computer science, like reachability and safety and bookie, they're all limsup functions, so they also fall into this category. And the last but not least reason to be interested in limsup functions is that you'll see them coming back in this workshop. If you follow Galit's presentation on day 3. They'll be serving as approximations of a given Borel function, in the sense that a value of a Blackwell game with a given Borel function will be approximated by a value of a Blackwell game in which the payoff function is the limsup function. So in fact, this is one of the results of Martin that appears in his 98 paper that these limsup functions could be used as such approximations. So these are the reasons why you might be interested in limsup functions. Now, what about this talk? Okay, one thing is to be interested in limsup functions. Another one is to spend your time listening to me. Well, I'll be playful. So I told you that this is about topological games, but today my emphasis will be on games. It's topological games with an emphasis on games. What I'm going to try to do is to a little bit suppress the topology and simplify it as much as possible, concentrating on game theoretic aspects. Now, what are these game theoretic aspects? Well, as we will see in 1 minute, literally, the definition of a limsup function is almost already a game. It's really a case where you don't have to invent a characterization that much. It's just there in the very definition. The game is very, very natural, in my opinion. And the second thing is that the proofs of in this paper, they feature explicit constructions of winning strategies. And some of these, I find, this is my personal take, don't forget, I'm a co-author of this paper, but I do find them elegant, and I do find them also instructive in the sense that you can learn from them. And I'll try to present these proofs perhaps not in every single detail, but certainly I'll try to present the gist of the argument. So this is my ambition for today. Notation. Again, I'll try to I try to simplify this as much as I could. So we have the space of infinite sequences of natural numbers. N in the power n. So n stands, of course, for the set of natural numbers. This is the set of infinite sequences of natural numbers. Topologically, this is the Baire space, so I might be referring to it as the Baire space occasionally. And you could also think of it as the set of plays. Okay. Elements of this space will be denoted most often by X, sometimes by Y. And okay, so that's just a sequence of natural numbers. And if I truncate this sequence at length t, then I get the prefix of such a sequence of length t. So xt is going to be the prefix of x of length t. Another piece of notation is this one. It's a set of plays or set of infinite sequences, y, that share the prefix of length t with a particular sequence x. Okay. Just as in Ron's talk.
Can I ask a question for
absolutely, Abraham. Yes, absolutely.
The O of xt, is it O of the sequence x and the index t? Do you mean for each x? Or do you mean it for every t less than something? It's not clear what is this notation.
Okay, so
I will call it O. The simple way that I understand. Sorry. I see that xt is the entire prefix. Okay.
xt is the prefix. Okay,
yes,
so
okay. Fact, sorry. I take back my question.
Maybe if you look at the
yes, okay, fine.
No problem. So I was about to say that, yeah, you can define this set O for any position P, for any finite sequence.
Fine. It's clear.
And these sets, just as in Ron's talk, these sets would form the basis of the topology on the Baire space. This is exactly the same as in Ron's talk. There's no difference here. But I'll need this guy here as well, which is the set of finite sequences of natural numbers with a notation n in the power smaller than n. Think about this as the set of positions. Okay, so the notation, but I think it will be self-evident for most of the time. Now, okay, we come to the main definition, that of the limsup function. So we're talking about a function f defined on the Baire space, on the set of infinite sequences, and we call it a limsup function if basically it can be written as a limit superior of something, or more precisely, if we can come up with another function called u here, defined on positions, defined on finite sequences of natural numbers, such that for any infinite sequence to compute the value of f of x, we take the limit superior of the corresponding values of u evaluated at the corresponding prefixes of the infinite sequence x. An example, a very simple example. Suppose that this u takes only values 0 or 1. Then also f takes only two values, 0 or 1. And think of this as a sort of in line with the interpretation of f as a payoff function. Think of u as a kind of the instantaneous reward or instantaneous indicator of whether our player wins a particular position or not, something like this. Okay, and if it happens that the player actually loses all positions except possibly finitely many, then we declare that this player also loses the entire play. Okay, and
is the function, sorry, is the function u on the top
no.
Is it to the power less than n? The finite sequences?
Typo. Yes. How about this? Yes, it's defined on positions. Sorry about this. Okay, so this is the true domain. And to say that our player wins the entire play, then the player has to be able to win at infinitely many positions. Okay, so a very tiny remark. You could be more general at a cost of 0. You could replace this entire set of finite sequences of natural numbers by any pruned tree, like in Ronstock, and then you replace the Baire space by the set of the infinite branches of that tree, and nothing happens to anything that I'm gonna say. I think I want to keep it simple, really simple, suppressing as many topological details as I can. But one I would like to briefly mention to you because Ron talked to us about Borel hierarchy, and so I would like to position this definition in this Borel hierarchy. And that I do with the help of a topological characterization. So the point is that limsup functions live very low in the Borel hierarchy. Okay, you see a very long theorem, but you don't have to pay attention to items 2 or 3. What the theorem says is the following: if you have a function f, then this function f is a limsup function if and only if its subgraph is a pi2 set. Okay, what's a pi2 set? It's also called sometimes a G delta set. Ron defined, yeah, so pi2 is going to be the second level of Borel hierarchy as defined by Ron previously today. The subgraph, what's that? Well, you can imagine what the graph is, and the subgraph is everything below. Okay. So this shows that the limsup functions are very, very low in the Borel hierarchy. Good. All right, so we now come to the second part of his presentation, which is really the main part. And this main part will be structured as follows. I'm going to introduce the game gamma of f. This is the game that characterizes when f is a limsup function. Really, more precisely, what this means is that our player 2, so we'll have two players, 1 and 2, and one of these guys, player 2, is the verifier. Player 2 will want to prove that f is a limsup function, and her opponent, player 1, is the falsifier. The falsifier wants to prove that f is not. Okay, so a criterion for player 2 to have a winning strategy will be almost built in this definition. Player 2 will have a winning strategy exactly when f is the limsup function. So that's why we call gamma a game characterization. But then we'll look at this game in more detail, and we ask, for example, when is it determined, and under what conditions does player 1 have winning strategy? So these questions will be more subtle. I'm going to present an overview, short overview of the results, consisting really of 3 theorems about determinacy of this game gamma. And then I'm going to focus on a sufficient condition for player 1 to have a winning strategy. This is a cool part, I think, because this is where an explicit construction of a winning strategy comes into play. I would be happy to present this. Okay, so that's roughly the outline of the second part of the talk. Here's the game called gamma of f. So we have 2 players, 1 and 2. Player 1 produces the moves that are natural numbers called a0, a1, and so on. So eventually, player 1 will produce a play. Player 1 will produce an infinite sequence of natural numbers. What does player 2 do? Player 2 responds with rational numbers, v0, v1, and so on. Otherwise, the game proceeds exactly like Ron described it. So player 1 makes the first move, player 2 reacts, then player 1 reacts to player 2's move, then player 2 reacts to player 1's move, and so on. Okay. So when does player 2 win? Well, player 2 wins if the following condition is satisfied. So let's look at the play that player 1 produced, and let's evaluate our function at this play. And then let's compare this to the limit superior of the sequence of numbers that player 2 produced. And if they're equal, player 2 is declared the winner. Okay, so player 2 basically wants to match the value of f at the play produced by player 1 with the sequence vt, where matching means that the limit superior of the sequence has to be equal to the value of f. So that's the idea. I think this is quite intuitive from the definition of the limsup function. This definition of the game really flows naturally from the definition of the limsup function, at least in my wicked mind, you could say. And the first lemma is really a gift in the sense that it's for free. Player 2 has a winning strategy in the game gamma of f precisely when f is a limsup function. The proof is literally this. Just start this game and we realize very quickly that player 2's winning strategy is exactly the same as a function u that we used in the definition of the limsup function. Right, so player 2 reacts to the moves of player 1. So here, for example, v0, player 2 could adjust depending on a0. v1, player 2 could adjust depending on a0 and a1. So player 2's winning strategy looks exactly like this. Okay, and it should be doing exactly this. Okay, no matter how player 1 is playing, the strategy of player 2 should guarantee that player 2 always guesses, always matches the values of f. So I would say this lemma is for free. Okay, so this is the game. Like run, we could also ask as our first question, is the game always determined? Are there games like this that are not determined? So we know from run that in principle there are games of perfect information that are not determined. Are games like this gamma of f, are they determined? Not always. So this is to convince you that also within this smaller class of games, there are some that are not determined. And here's my first result, which is basically that, okay, there are games that are not determined, and you can construct one like this. If you take B to be a Bernstein set, then the indicator of B, which is a function, okay, for this indicator of B, the corresponding game gamma is not determined. This stuff, I would say, is not terribly important. I tell you in 1 or 2 words how to construct a Bernstein set. It's actually not very difficult if you give me the axiom of choice. That is, if you give me an enumeration of all real numbers, a well ordering of real numbers, I'll be able to give you a Bernstein set back. Okay, so what's a Bernstein set? It's a set with the following property. Neither the set itself nor the complement of the set contains any uncountable closed subset of the Baire space. Okay, so it's a kind of a set that hits every uncountable closed subset of the Baire space. Like in Ron's construction, you need axiom of choice to build one. With the help of the axiom of choice, it becomes relatively easy. What we do is the following, roughly speaking. We just enumerate all uncountable closed subset of the Baire space. Where enumerate, by enumerating, of course, I mean enumerating using ordinal numbers. And once we enumerate them, we just go over them one by one. And what you do, every time you take a new uncountable closed subset and pick a pair of elements from it, a new pair every time. And you add one of these to the would-be Bernstein set, and you add the other one to the complement. And you grow the Bernstein set and its complement recursively then. So that's roughly the construction. I do have the details, but perhaps this is not something I would like to focus too much on, unless you tell me that this is really interesting and you want to hear the details of this construction. If that's not the case, then I think we're safe to just assume that this works, and certain games are not, certain games like this are not determined. Okay, I don't hear any objections, ladies and gentlemen, so I just move on to the next slide. Okay, so when are these games determined? When is gamma of f determined? Well, I could just ask Martin, and Martin will tell me, well, surely if f is a Borel measurable function, if f is Borel, then gamma of f is determined. Why is that? Well, that's by Martin's theorem, the one that Ron presented. So this is really a direct corollary. However, yeah, the paper doesn't stop here. We would like to be a little bit more demanding and establish determinacy beyond the cases where f is Borel. So ideally, yeah, I would like to say more. And in fact, this is one of the results that we have. If f is the so-called semi-Borel, then the corresponding game, gamma of f, is also determined. Now, what's semi-Borel? Semi-Borel is when the subgraph of f, that is the set below the graph, is a Borel set. Okay, so
can you maybe give an example of a semi-Borel function that is not Borel?
That, Abraham, that would be difficult. That wouldn't be easy, I think.
Okay, so let's go on.
Let me try to go on. So, okay, so this is the theorem that I have in mind. However, what we're going to do next is that we are going to sort of approach its proof, but not entirely complete it. Why is that? Well, because what we are going to do is explore the question of whether and when player 1 has a winning strategy. So recall that we have a sort of a free characterization of when player 2 has a winning strategy. Okay, that was easy. But we would like to have something like this for player 1 as well. And this is the part of the paper I'd like to elaborate on. I'll get some chat messages, I think. There's no draw. No, there's no draw in these games. Ah, Martin, hi. Yeah, so when f is not limsup, then such a u doesn't exist. But that's exactly that's almost exactly the definition of what a winning strategy is for player 2. Yes. What is less clear is a condition under which player 1 would have a winning strategy. That is absolutely less clear and less trivial. And that's the question that I would like to spend some time on. So in this direction, we have two results, A and B, and we identify what I call here in this slide a Hurewicz condition. So our first result is sufficiency. Hurewicz condition is sufficient for player one to have a winning strategy. So this is true for an arbitrary function f. The theorem says let f be an arbitrary function. If the Hurewicz condition holds, then player one has a winning strategy in gamma of f. There's also the converse to this theorem, but it's only a partial converse. The Hurewicz condition is not only sufficient, but also necessary for player one to have a winning strategy in gamma of f, but that we can show for functions f that have finite range. As a matter of fact, we're a little bit more general than this, but not really much more. This is only a partial converse, and we know that in general the Hurewicz condition is not a necessary condition for player one to have a winning strategy.
I have a question.
Sure.
If f is not 0, 1 valued, then do you mean that it's a winning strategy or an optimal strategy?
I just mean a winning strategy. Okay, so it's the strategy.
You mean a strategy in this? Okay.
It's the strategy in the game gamma of f. I don't have any other games so far in my talk, but there'll be lots of games in this workshop. So I'm talking about player one's winning strategy. So remember, player one is the guy who is the verifier. So his goal is to prove that f is player one is the falsifier. Player two is the verifier. Player one's goal is to prove that f is not a limsup function. Okay. And so his winning strategy would guarantee that no matter how player two is reacting by choosing the sequence v, this equality is false. And hence I call player one a falsifier. So it's really just the winning strategy in the game gamma of f.
Okay.
Yeah. Thanks for your questions, Abraham and Martin. If you have other questions, you may want to just speak out like Abraham does, because it's a bit hard to keep track of the chat. Okay, so let's go back to theorem A. Before I can, say more, maybe I should tell you what this Hurewicz condition is. So here's the condition. There's a number R and a set C living in the Baire space, in the set of plays, with the following three properties. C is closed. It doesn't have isolated points. Now, what's an isolated point? Well, it's very intuitive. So basically, it's a point which is alone in a certain neighborhood. Okay. The second condition speaks about the set of plays where f is at least R. And what it says is that the intersection of C with this set, where f is at least R, is a countable set. It has to be a countable set. And going forward, I'm going to enumerate elements of the set as x of 0, x of 1, x of 2, and so on. So it's a countable set. And the third condition says that this set is dense in C. Okay, so I did my best to provide a picture, to provide an illustration, and maybe go some way towards sort of illustrating this condition, but you'll see why it's not easy. Okay, so what do you see here is the best space. It's the entire set of plays. And here on the right are those plays that where f is at least r. And here on the left are those where f is smaller than r. You also see the red shape. That's my set C. Okay, so my set C is supposed to be a closed set without isolated points, and that's why these dots are sort of might be slightly misleading. They seem to be hanging there alone, but they shouldn't, because no point of C is isolated. But what I wanted to illustrate is that the second condition, really, the intersection of C with the set of plays where f is at least r has to be a countable set. And what's moreover true is that this countable set is dense in C. So that means that if you take any point in C, then you can approximate it by these elements, x of 0, x of 1, x of 2, arbitrarily well. And that's very difficult to picture. Okay, but here is the condition. Okay, so we come to, I think, an exciting part of the talk, because I'm going to prove theorem A, which says that this Horevich condition.
I have a question.
Yes,
Can you give us? You could have written the same condition without the sequence. What is the role of the sequence? Is it going to play a role later, the enumeration of the points?
Yeah. Right now in the proof. I'm preparing, I'm paving the way for the proof. Yes. Right now I could just suppress it. Yeah, you're absolutely right. Yes. And so the proof of this. Yep.
Arkadi, what was the motivation of Horowitz to come up with this condition?
A characterization of G delta sets. It's a characterization of G delta sets. Or rather of F sigma sets, so pi to sigma 2. There's a theorem by Horevich which says that if you have an analytic set, then it's an F sigma set if and only if it's an F sigma set if and only if I can find basically a set capital C with these three properties, where you replace this guy by the set you're interested in. Okay. The condition comes from the Horevich theorem, which provides a characterization of the F sigma sets. At least if you know that the set you are handling is an analytic set. But yeah, we just took this literally and we used this result. All right, so I would like to present the proof. So under this condition, player 1 has a winning strategy. Okay. So here's what it does. You start like this. So you take the point x of 1 right here, and you start zooming in on it, which means to say that you're just following this sequence, x of 1. You're awaiting a stage n0 with two properties, of which the second one, I can tell you right away, is more important. The first one is sort of automatic. So the first one just says that you have to wait for long enough to exclude x of 0. Okay, to exclude x of 0. What does it mean that you exclude x of 0? It means that you have to wait for a stage n0 where the prefix the corresponding prefix of x0 is already incompatible with the corresponding prefix of the play that you are following. And so that means that by the time you've reached this stage, you know that x of 0 can no longer happen. It will not be the play that you produce, because already by this stage, you made a move somewhere that's incompatible with x of 0, okay? And because I'm implicitly assuming that all these points in the enumeration are different, such a stage, the stage satisfying condition A, surely comes. So that's really not a big deal. You just have to wait for long enough, maybe. B is important. This stage, it has to be the one where player 2 decides to make a relatively large move. Okay, so here the move, which is at least r minus 1. Okay. That gives you a hint intuitively that sort of player 2 perhaps is going to produce a sequence V with a limit superior, which is relatively high. And then what you want to do is you want to avoid being in this set. So at this stage and 0, what you want to do is you want to stop following x of 1. You want to stop zooming in on it, and you want to start doing something else. So what do? You choose one of these points, numbered k1, different from the one you followed before. And well, this just says that the k1 you choose is such that the corresponding point x of k1, it has to be feasible. It shouldn't be excluded. So you should be able to switch to it after this stage and 0. Okay, but that's possible. That's possible because none of these points are isolated, and this set is dense in C. So any point from this set can be approximated arbitrarily well by some other points. Okay, so I can always switch to something else, and that's what I want to do now. I want to switch to the play K1. And then that's what we do. We switch to zooming in on this other play, x of k1. It's a point somewhere here, the one we've chosen before. And we do so awaiting a stage n1 where two things are true, of which the second one is sort of more important than the first. It's the stage where the point x of 1 is already excluded in the same sense as before, that at some point you've made a move which is incompatible with x of 1, so that the prefix of length n1 under x of 1 is already not the same as the prefix of this play you are currently following. And condition B says that this is a stage where player 2 makes a still higher move. So player 2 really wants to raise maybe his limit superior of the sequence V, and so she plays r minus 1/2. And that gives you that's an alarm bell for you to switch. If such a stage comes, you don't want to follow x of k1 any longer, you want to switch. And you switch to the point x of k2. Any other point different from x of 2, but that is still possible to switch to, in the sense that, yeah, it's still feasible. It has the same prefix of length n1 as the point you've been following until now, which is x of k1. This is what the general step looks like. So you are at the beginning of the step, you are zooming on a certain point x of km chosen previously, and you're awaiting a stage, let's call it an M, where the point X of M is excluded. Okay, so at step M, you're waiting for the point X of M to be excluded. So to reach a stage where the current prefix is already incompatible with the corresponding prefix of X of M, and where player 2 makes a really large move. So where V and M is very close to R, basically. Is at least R minus half in the power M. And then you don't want to follow X of Km any longer. You want to switch. And the way you switch is this. You pick any element in this countable set other than M plus 1, which is still feasible. And you pick anything else than M plus 1 because you will want to exclude M plus 1 if need be. Okay, so let's see why this is a winning strategy for player 1. So we need to deal with two cases. One is the case where player 2 produces a sequence V with the limit superior smaller than R. What happens then? What happens then is that player 1 will not get over a certain step, let's say step M. Why is that? Well, because you only get over a step M when the move of player 2 becomes large relative to R. But if limit superior of the sequence that player 2 is building is smaller than R, then there'll be a step, that never comes. And that means that you will never switch here, and that means that you'll be following X of Km forever till the end of the game. You'll be following X of Km forever. That, of course, means that you'll be building this as the outcome play, X of Km, and it's a part of this countable set. And in particular, it's a part of this set. So here, the value of F is at least R. And you won, because the limit superior is smaller than R, but the value of F at the resulting play that player 1 has built is at least R. Case 2 is the case where the limit superior is at least R. In this case, this sequence triggers player 1 to switch infinitely often between the steps, because player 2 will be sort of edging towards R or even higher, and every time this will trigger player 1 to switch. Recall that every time that player 1 switches, she excludes a certain element of my countable set. So at step N specifically, she is waiting to exclude X of M, and she switches only then. If she goes through all the steps in this construction, then eventually she'll be excluding them all. Okay, so that means that she'll be hopping from one set here to from one play here to the next, every time waiting for well, her target play to be excluded in this sense. And that means that,
shouldn't you choose Km plus 1 to be the minimal index that is consistent with the current position?
Yes, perhaps. I'm not sure if that's important, but that will work. You should choose it to be something else than M plus 1 to be able to exclude it.
Because if it is very large, then you may miss some X in the middle. You just skip some X, which is actually the play that is generated. I know.
That's okay. You really want to hop from, so I don't think it's important. You just want to hop from one X to the next, not in this case, in case 2, okay? Not zooming in one particular play forever. So you want to switch infinitely often. But every time you switch, you want to exclude. So if you switch 5 times, then you want that by the 5th time you switch, you've excluded the first 5 elements of this set. And by this time you switch 100 times, you want to have excluded the first 100 elements of this set. How you exclude them is not really important, I think.
Okay.
By doing so, you just guarantee that the resulting play that you are building is not any of these X of M's, because you excluded them all by your hopping from one to the other. However, the resulting play will be in the set C. It will be in C. Why is that? Well, because all the things you're hopping from and to, these X of Km's, you're following, maybe not all of them, but you're jumping from one X of Km to the next. And they're all elements of C, and C is closed. And that means that basically you'll be staying in the set C in the limit. And that means that Y will be in C despite not being any of these countably many elements. But let's look at the top line here. What does this mean? Well, this means that, okay, so Y is in C, but Y is not in the right-hand side. So that means that Y is in the set of among the plays where F is smaller than R. So you fooled player 2 again. Player 2 constructed a sequence with the limsup of these, which is at least R, and you've constructed a play with the value of F smaller than R. Okay, so you managed to mismatch. So this is the construction, and that's why it works. Okay, I taught you how to fool player 2. Basically, that's what is going on here in this proof. So, okay, I really don't expect that okay, so some of you will be able to follow this entirely, but really, if I were you, I don't think I would be able to follow the details, but I hope that I conveyed the gist of the argument a little bit. That was theorem A. Now, what about theorem B? So theorem B says that this Horevich condition is also a necessary condition for player 1 to have a winning strategy. And theorem B works if we know that F has a finite range. So I would like to illustrate sort of why this is true, but only in the most rudimentary case where F is 2 valued. Okay. F is 2 valued. And really, I'm doing so to illustrate maybe the interplay between topology and games. Okay, that really is my main motivation for doing this. This is another sort of game theoretic proof almost. Okay, so what do we assume? We assume that F is 2 valued and that player 1 has a certain winning strategy in this game. Player 1 is the falsifier. Remember, player 1 is the player trying to disprove that F is the limsup function. Okay, so let's fix one winning strategy for player 1. And this is really the key here, that any winning strategy of player 1 induces a continuous map called G here. What's that? Well, it just maps the sequence of moves that player 2 produces into the corresponding moves that player 1 has to produce as a response. Very natural. And it's a continuous map. It's a continuous map. Actually, you could say even more about it. But in particular, it's a continuous map that transforms plays of sequences produced by player 2, these sequences of rational numbers into plays that player 1 produces using the winning strategy. And I'll try to convince you that this Hurewicz condition is going to be satisfied if you choose R equal to 1, and if you choose the set C to be the image under this map G of the set K. What is this set K? Well, it's the collection of sequences of binary numbers, 0 and 1. So basically, we just discard all moves of player 2 except 0 and 1, which makes sense because F takes only 2 values, 0 and 1. So let's imagine that player 2 only plays 0 and 1 ever. So then K will be all possible infinite sequences that player 2 could build. And C then is the image of that under the winning strategy of player 1. And here's why this works. Okay, so on the left here, what you see is all possible sequences of moves of player 2. We restrict attention to these binary moves, maybe. And on the right are all the possible plays that player 1 can construct in response. And so G would map the space on the left into the space on the right somehow. Now remember, player 1 is the falsifier. So she wants to mismatch the limsup. And that means that the sequences of player 2 where limsup is equal to 1, they have to be mapped inside this set where F is 0, and vice versa. The sequences of moves of player 2 where the limsup is 0, they have to be moved by the winning strategy of player 1 into this part of the space where F is 1, so that always there's a mismatch. Okay, so the G has to work like this. Okay, L0 has to go here somewhere, and L1 has to go here. And together, the image of G, it's this set, this is capital C, and that works. So let's see why this works for the Hurewicz condition. Okay, the first bullet point is what you've seen already on the previous slide. Li is just the sequences of moves of player 2 where limsup is equal to I. I could be 0, 1. One thing is important about L0. L0 is countable and it's dense. So why L0 is countable? Because basically it just consists of sequences that are eventually 0. Okay, that are eventually 0, and that's a countable set. And also it's a dense set in K. You can approximate anything by points like this. The third bullet point is what you see on this picture. This is the winning condition for player 1, for G, really. It just says that G comes from the winning strategy. It just says that L0 has to be mapped here and L1 here. That's what I explained. And also, G of K has no isolated points. Why is that? Well, this has nothing to do with topology. This is coming from the fact that G is a winning strategy. If that were not the case, then it would mean that after a certain stage, player 1 stops reacting to player 2. Right? So if G of K has an isolated point, then it means that, remember, this is the possible reactions of player 1 to player 2's moves. And if there's an isolated point, it means that after a certain sequence of moves of player 2, player 1 just produces the same sequence, no matter how player 2 plays in the sequel. And of course, that's not compatible with G being winning. It's kind of obvious. Player one always has to react somehow. Okay. I hope I was a little bit convincing that this is not possible. That's it. Basically, if you sum up all these facts together, then you conclude that G of K is the set that works. It's closed, it has no isolated points. The intersection with F, with the set of plays where F is 1 is exactly G of L0, and it's countable because L is countable. And G of L0 is dense in G of K because L0 is dense in K. Okay. This is a rather typical thing in topological games, that if a player has a winning strategy, you would want to think about this continuous map and say a couple of things about it. So in that sense, this proof is somewhat representative. Okay, so yeah, so we've done these two theorems about player 2 having a winning strategy, and of course you can see that there's a gap between theorem B and theorem A. Here F is assumed to have finite range. And it's an open question. What kind of a condition could characterize player 1's winning strategies in our game? We don't know. We don't know. All right, ladies and gentlemen. So if you are still there, that's a great point to ask questions about the second part of the talk. Just shout at me.
Yes, Arkadi, I have a question. Exactly at that slide, is it clear that the G map can be chosen for player 1 independent of what he has done in the past? So that, that it's continuous and everything. I would have thought that, what player 1 needs to do at step 100 depends not only on the values of player 2 that player 2 has chosen, but also what he himself has done in the first 99 steps.
Sure.
And what you're saying, it seems that it isn't, because it's solely a function of what player 2 does, right?
Martin, in principle, you are right. But I was a bit careful here because I said that the winning strategy of player 1 induces a continuous map. So I wouldn't, they are not exactly identical things. So yeah, so of course, a winning strategy of player 1 might well take into account what player 1 has done. But in building this continuous map, of course, you only want to be consistent with your winning strategy. So you discard all the moves that are not consistent with it. We're talking about pure strategies. So you know exactly what you have to do at every stage. So if at stage 0, the winning strategy tells you to play 0, then you should play that, and that builds into the definition of this continuous map. You don't want to insert, you might well think what would happen if you play 1, but that's not what you want to do to construct this continuous map. Okay. Right, so this is also quite typical. So in fact, in these Martin games, you don't need to define strategies the way game theorists do, because you're only interested in winning the game. Of course, as soon as you start being interested in winning sub-games, now it's important that the strategy is defined on all positions. But okay. Here, you're not interested in winning sub-games because you don't assume to ever reach a sub-game where you're not winning. You don't assume to ever deviate from the prescription of the winning strategy. And I think that's the way to explain why you can always sort of think about a winning strategy as a function that only depends on the moves of your opponent.
Okay.
unless you're interested in subgames, which I'm not at the moment. And mind you, later on, tomorrow and the day after, people will be interested in subgames, then it changes. Then I agree with you.
Yes.
And here is just not important.
I have a comment and two questions. First of all, the comment, you say it's not the concept of a strategy that game theory are taking. So there is a concept which is called reduced strategy, which goes back to the 50. So if you think of reduced, what you are doing here, you are interested in reduced strategy. So that's completely kosher. Can you go for a moment to the statement of the two theorems or the definition of the game? Even go to the definition of gamma of f, to the description of the game. Okay, so here, this game, the function limsup, as you mentioned, is low in the Borel hierarchy. You could go a little higher in the Borel hierarchy, and instead of saying pi to 0 and take a little higher, is there something that will be similar to an Horowitz condition for functions in one step higher in the hierarchy, or something that connects the hierarchies of the Borel to this type of theorems?
Thanks, Abraham, for your very deep question. Yes, so I'm not sure about limsup, but if I go back to the beginning of my talk, this paper, I believe, has a characterization of functions in the Baire class N. And I have not included, but there's also a paper by Victor Kish with a game characterization of, or some characterization of functions of an arbitrary Baire class. So that certainly is not impossible. And there is this dissertation which also gives game characterizations of functions of the higher order of Baire or Borel hierarchy.
And now a question, the second question is to everybody in the audience, or to you, whoever knows, both in your lecture and Ron's, it was mentioned the important role of the axiom of choice, both in the counter examples and in the proof. It is known that if you reduce the axiom of choice, then the Martin determinacy could be defined, could be added as an axiom to each subset of the 0, 1, if I'm not wrong.
Axiom of dependent choice, I think, right?
Sorry?
Axiom of dependent choice, I think.
Yeah,
that's the level.
Is not contradicting the other axioms of the Zermelo-Frankel. And I think recently, and here, if somebody knows more details, I would be happy to hear. Recently, there was some work by logicians on the relation between the Martin determinacy axiom and the continuum hypothesis. If somebody knows more details about it, I'll be happy to hear. Have you heard about something like that? I think whether Aleph is Aleph 1 and the axiom of the determinacy. Okay, so I'll try to get to read the email that I got on this issue, and maybe if I'll understand it better, I could make a comment in one of tomorrow or so. Yes, but there was some work, I think a breakthrough on this topic.
Thanks, Abraham. Well, I'm afraid I have nothing to say on this, but I did have something to say about Baire class 1 functions. That's a typical, that's a typical classical stuff of set theory. And this is what I wanted to say. I'm not sure I'll have time to say it all. I'll present a game that characterizes these Baire class 1 functions in some sense, in a very strong sense, as a matter of fact. Now, firstly, what are these Baire class 1 functions? Well, one way to define them is as functions that are pointwise limits of sequences of continuous functions. So you have continuous functions, and then you take pointwise limits, a pointwise limit of a sequence of continuous functions. What you get is a function in the Baire class 1. However, this is one of the possible definitions. For our purposes, the following is maybe a more convenient definition, or if you like, a characterization of a function in the Baire class 1. So in fact, f is in the Baire class 1 if and only if both f and minus f is a limsup function. Now, of course, instead of saying that minus f is a limsup function, I could have said that f is a liminf function. Okay. Well, this also shows that the definition of a Baire class 1 function is symmetric in some sense. The definition of a limsup function is not obviously symmetric. This one is. And this characterization, again, it just leads us to game characterization immediately. So that the game characterization flows from this very naturally in my wicked mind. So here it is. The game is called gamma prime, and it's very similar to the game I presented before, with the difference that now player 2 is producing pairs of numbers, v and w, every time, not just one number. And player 1 plays as before. And player 2 wins the run if she double matches. So as before, the limit superior of the v sequence that she constructs has to be equal to the value of f evaluated at the play constructed by player 1. But at the same time, the limit inferior of the sequence of W's that she builds, it has to be equal to the same thing. Okay, so her task is more complicated. As before, player 2 is the verifier and player 1 is the falsifier. So we get this result. Again, for free, if you take it for granted what I told you about f and minus f. Player 2 has a winning strategy in the new game, gamma prime of f, if and only if she has both a winning strategy in gamma of f and one in gamma of minus f. And that's the same as saying that f is a function in the Baire class 1. In the Baire class 1. As was the case with the game gamma, this is really a costless result. It's almost for free. So what about player 1, and what about the determinacy of this game? And here you might be surprised because we have this. Unlike the game gamma I've presented to you before, this one, gamma prime, is always determined. It doesn't matter what f is, whether it's Baire or semi-Baire or not. The game gamma prime of f is always determined. Now the difference, I must have a confession to make. This difference between the two games in terms of determinacy, because one is always determined, the other one is not always determined, it still baffles me a little bit. If you ask me for an explanation, well, I think I'll be in a difficult position. There's something about, these Baire class 1 functions that makes them easier to characterize using games in some sense. Okay, in the little time that I have, I would like
I am not sure that I understood that, you maybe I missed something before this slide. So this is the game. Here is the description of the game gamma prime of F.
Yeah, it's a different game than before. It's not the same game.
Yes,
in this game.
So player, yes, I understand the game. Player 2 chooses the 2. So player
2 has more. So player 2 now has to choose 2 numbers, not just 1 number, every time, at every stage, a pair, V and W. And his task is more difficult than before.
Okay. Now I understand the theorem. Yes. Okay. So what does it mean for any function f? It is determined. That's the conclusion.
It's
no need of any Borel or something or
no Abraham, no need for any assumption. No need for any assumption. Of course, if f is Borel measurable, then we could apply Martin, and then it's a costless corollary that the game determined. But the point I'm making is that we do not make any assumption on f whatsoever. The game is always determined. I cannot present the entire proof of this result, but maybe I could give you a gist of the argument. So the key here in proving this will be looking closely at player 1. So about player 2, we know everything. So player 2 is the verifier. It's easy. She wins the game exactly if the function is in the backlash 1. Well, for player 1, it's not so obvious. Okay, so Fox, this becomes maybe more heavy and more complicated, but I'll try to explain intuitively what's going on. We have basically a necessary and sufficient condition for player 1 to have a winning strategy in the game gamma prime of f, a necessary and sufficient condition. And this condition has to do with the concept of oscillation. I think the concept of oscillation is a bit intuitive. So fix the set C of plays and look at the restriction of f to that set C. We are going to measure the oscillation of f around the point x. And roughly speaking, the oscillation measures how widely f fluctuates around the point x. So what you do, you first fix an open neighborhood of x, and then you just take the difference between the highest and the lowest value, that f could take within that neighborhood. Okay. How big is this gap? And then you zoom in on the point x, taking smaller and smaller open neighborhoods of x, and look at whether this gap, how much it decreases. If your function f is continuous, then this gap is going to disappear, and the oscillation will be identically 0 at any x. But in general, not at all like this. So roughly speaking, this is the measure of how widely f oscillates around x. And the condition is this. There is a closed set C such that if we restrict f to C, then the oscillation of this function is bounded away from 0, like this. Okay, so knowing that I will be short on time, I've prepared an intuitive explanation of the proof, and I'm going to present only that. It's a proof of the sufficiency. The proof of necessity is topological. I did not want to talk about it. The proof of sufficiency is game theoretic. And so I'm going to go over this intuitive overview, which is 1 slide, and give you, hopefully, convey the intuition behind this. Okay, so suppose that we have such a C where the oscillation of F is bounded away from 0. Player 1 is going to have a winning strategy, and he is the strategy that's going to be winning. As in my first proof, player 1 is going to be sort of hopping from one play to the next, but he'll be going through two types of switches that I call odd and even, because yeah, okay, so two types of switches. At the odd switch, what player 1 is doing is this: he'll follow a play with where the value of F is very high, and he'll just be zooming in on that play. And he'll be zooming in on that play until possibly a stage where player 2 makes a move where V is very high. And at that stage, player 1 wants to switch. She will choose a different play to follow, where the value of F is basically as low as possible given the position that's been reached at this point. And she will start following that particular play with a low value of F. She'll start zooming in on it. And she'll be doing so until a stage where player 2 makes a move where W is very low. Okay, and once such a stage is reached, we go back to the odd switch. So she'll choose a play with a very high value of F, and we'll start zooming in on it. You can sense intuitively, I hope, that this behavior, what it does, it drives a gap between V's and W's. And this is possible because the oscillation of F is bounded away from 0. So the high values of F are always somewhat higher than the low values of F. Okay, they never collapse. There's always a gap of 5 epsilon actually between them. And player 1 makes sure that the moves of V, some of them are very high, and they're sort of close to the upper range of F. And the moves of W, some of them are very low and close to the low values of F. And that means that basically player 1 will make sure that if she goes through all the switches, that the limit superior of V is always higher than the limit inferior of W, thus, yeah, thus winning the run. So that's the intuition behind the construction. Amazingly, I have 1 minute left. I have that 1 minute to say thank you to all of you, to all those of you who came here and for having me here, and also, of course, for your very interesting and challenging questions. So thanks very much.
Thank you.
Thank you. Questions, remarks, colleagues?
Okay, now I want to see you. How do I? No. How can I?
Yeah, could one very vaguely say that you know, your second stronger theorem, where you have determinancy, basically comes from the fact that now it's easier for player 1 to falsify, basically.
Well, I think the second statement is true. In the second game, player 2 has a harder task, so player 1 has an easier task. how this implies that the game is determined is a bit more difficult for me to explain, even though I must add that there are other results, for example, by Victor Kish with a different game, characterizing functions in Baire class 1 that is likewise determined always. It's a different game Victor has, not the one I presented, but the result is a bit similar in the sense that, well, it also says that whatever function you give Victor, his game is always determined. Either player 1 or player 2 will have a winning strategy. So it's something about Baire class 1 as opposed to limsup functions.
Mm-hmm. Okay. Do you have some intuition why it's so hard to understand the good strategies for player 1 in the limsup functions?
Yeah, one is that we're all humans. Our ability to comprehend is limited. This is true of me more than of my co-authors for sure, who have deeper insights into this. But it did take us a long time to go from a 2-valued f to 3-valued f, believe it or not. Okay. That was not an easy step. You would think that if I have a 2-valued f, then for 3-valued f is going to be easy. No, it was not. The theorem B, which is necessity, is a little bit more general. It says that if the range of f does not include an infinite ascending sequence, then we are fine. And that generalization, so from a finite range to this slightly more weaker condition on the range, that was also a difficult step, not an easy one. Probably we need a condition which is in the spirit of Horevich, but that is applied to the somehow the subgraph of f or the graph of f. Somehow the one we have sort of operates on the set of plays. It says something about subsets of the set of plays, but maybe the condition, the good condition, the one that always works, has to lift this to the space where the graph of f lives. So Baire space times real numbers, and somehow applied there. This is roughly my intuition. I'm not just so. I think something like that possibly could be done. There's nothing that tells me that such a condition cannot be developed, let's say. Quite on the contrary, actually.
Okay, cool. Yeah.
So thanks a lot.
And okay, sorry, Arkadi. So you always consider real valued functions. So what if you don't consider real valued functions, but something abstract? So what are the properties reflected of the real line reflected by this payoff function you really use? So do you have any idea about it? What will happen? It will be something more general or just different range of your functions? I don't think, of course.
Miklos, thanks for this question. How should I start by? So, okay. Let me go back to the literature. So the first paper that you see here by Kairoy, I think it's a characterization of the first Baire class for functions that take values in the real line, like in my talk. But Victor's paper, this one, is a characterization of Baire class 1 functions mapping an arbitrary Polish space into another Polish space. Okay, so that's already a part of the answer. You can do something like that, but you need a different game. Limsup functions, on the other hand, are naturally defined for real numbers. So it's just a definition that already triggers some kind of at least an order, right? So to be able to speak of limsup of something, you probably need some kind of an order at the very least. Now, the most natural example is real numbers, of course, but I could imagine extending this to domains where you could still sensibly talk about limit superior. I don't know, maybe some kind of a lattice.
Okay, thank you. Thank you. Further questions, remarks? Not, then thank you again.